Okay, so let's get started for today. I made a post on Brightspace last night. Hopefully most people saw it. And my observation of this test was let's see, the class didn't do as well as I thought everybody was going to do. I kind of stand by this test. I really believe this was a fair test. Just to really quickly go through it, explain the effect of shielding. That's what we did in class when we passed out the sheets of tinfoil, and we talked about the field inside the conductor being zero. The equipotential lines being perpendicular to the electric field lines. That comes from the dot product. Delta V is E dot delta S. And we talked about that kind of at length in class. This question, you might want to start jotting down a few notes as I'm speaking. These things might feel a little bit more relevant in 2 or 3 minutes. With this question, this was where we talked about the resistance of an object, R equals rho L over A. You had to apply that twice in this question and you could find the answer. For this one, I felt like this one was fair. It came straight off your assignment. So that was kind of ditto. Like I literally copied and pasted, so just cut and paste straight from your assignment. So I kind of felt like that was fair to ask. This was a twist on a capacitor network. So this would have taken a little bit of thought, certainly. These two are in series. You know the equation for capacitors in series, so you could write down that equation. You'd have to leave C as a variable because you don't know C, right? So these two are in series. You could write down that equation. That equivalent right there, that equivalent and this one, those are in parallel. You know the equation for two things in parallel, so you could write down that equation. And you know that that has to be equal to 10.1. So when you wrote out your full equation, the only thing you wouldn't know would be C. Okay, so you could do your math and figure out your C. For your potential energy, you just use the equation for potential energy. And then if the 7.22 is increased, what happens to the energy? Well, what you would do is you would look at your equation for potential energy, and you would see how that resistor came into play. If you weren't totally comfortable with that sort of theoretical approach, you could just put in, redo your workings. Instead of using 7.22 microfarads, put in 10 microfarads, right? See what happens to the energy. You could literally make it bigger and see what happens. And then the last question, I do recognize that this one is definitely a thinker. However, we did the solid sphere in class, and we took our time and went through it, all of the steps. We did the solid shell in the problem session, and I put it on the board. Once I put it on the board, I did try and give a pretty heavy hint. I said, now that I'm doing this on the board, this is totally fair game for a test. The only tiny twist was that I put an extra point charge in the center, so you had to think about that point charge impacting the electric field. So I do believe it was a fair test, I really do. And I believe it's reflective of the things that you should be able to do in this course. It is part of the learning objectives that you can do things like this. Because there's kind of a discrepancy with how you did and ideally how I would have liked for everybody to do, I would like to offer an extra credit work for this test. The extra credit work does come with some rules. Rule number 1, this is my hill to die on. I am going to take this really seriously and I am going to apply it. If anything for this test shows up online, if I can search for it and find it, all of the extra credit is withdrawn. If even one student posts this to Chegg or Bartleby or study.com or any of those sites, Ask Physics, Quora, any of them, if I see it online, then nobody in the entire class gets any extra credit. Okay, I do mean it, I'm serious. I know a lot of people don't think those sites are cheating or there are any problems. I see it as a problem, so this has to be your own work. The purpose is to give you an opportunity to go through this material and make sure you really get it. So that's why I want to offer the extra credit, is to give you the chance to go sure and make sure you can really master all of this work. I think it's really important. So here's the deal. To get the extra credit, you have to take your test and you have to redo the test. Okay, so you have to redo it entirely, all 4 questions. And then the deal with redoing it is they have to be done right. So this is not going to be a partial credit business like a test in a test environment is. This is going to be right or wrong. So to get the credit, you've got to do it right. Okay, it feels like a big ask, but you are allowed to get some help. If you do it correctly, then I'm going to adjust your score on test 2. So whatever you got, I'll go in and I'll change it based on this extra credit. The way the score adjustment works, and I thought for a long time about this, and this is the scheme I came up with. What we'll do is you can earn back up to half of your missed points. Okay, so the people who got a low grade, it looks like there was a bunch of stuff they missed, so those people might have to work a little harder to get this done exactly correctly. If you're working harder and doing more, you're going to get more points back. So for example, if a score was 20%, it means you were 80% away from 100. If you redo the test, you get it all right. I'm not going to give you the full 80% back and let you have 100, but I will give you a half of 80. So you'll get 40 extra points added to your score of 20, so you get a new score of 60. If you got a 50, then you were 50 away from 100. You can earn back 25 points. That can bring you up to a 75. Okay, so the extra credit will take you halfway between a perfect score and what you got, essentially. So that can bring everybody's mark up to a place where I hope they're going to be happy with it. And then here's just a sample of what the scores would be. Like, I think you guys can figure that out based on your own score, but that'll take you close enough to it. It's going to be due noon on Friday, so kind of at the start of class. If you want to do it beforehand and bring it to my office, no problem, doesn't matter, whatever. Paper copies only, so no electronic submissions. If you say, I'm sorry, I'm not coming to campus, here it is by email, I'm sorry, I'm not going to take it. Paper copies only. If you think you're not going to be on campus on Friday, then you should make every effort to get it to me on Thursday. If you come by my office and the door is closed, just slip it right under the door and I'll be able to pick it up. You are allowed to have some help. I encourage you to get some help. It is important to be able to do these things. So you can use your textbook, you can use your class notes, you can use your notes from the problem session. So all of your notes are completely fair, no problem there. You can go to the help center. That's open between 10 and 3, Monday to Friday. So you can drop in there. It's staffed with good people who can help you with all this work. You can explain the deal that you're redoing the test in order to get extra credit. And they can help walk you through all the bits that you aren't so sure about. I kind of heartily encourage you to work with each other. There's a lot of learning that happens peer to peer. So I would sort of encourage you to pick a spot where you could work together, you know, up in the help center or over in the UC or another place. And I would really encourage you to get together and talk about the problems. You know, if you put a few people together, then you each got different parts correct and you each understand different parts. So a group of 6 people can certainly get it all right together. You can come and see me. I've got official office hours, but I think most people know that you can drop in anytime my office door is open. I will take you through this. I want you to get it. I want you to understand it. I don't mind going through these problems with you. So you can come and see me and I will help you with it. As you work with other people, I would just remind you that you can't copy from person to person. We can't have one person redoes the test entirely correctly and then passes it to the next person who copies it off and passes it to the next person that copies it off and so on. So that sort of copying from person to person, that would be called not cool and you wouldn't get any extra credit for that. You can certainly work together and share your ideas, but when pencil goes to paper, you're writing down your own thoughts in your own way, so no direct copying. Okay, the floor is open to questions.
What are we supposed to write this down on, like our previous test that we got back today, or like a piece of paper?
Fresh paper, please.
Okay.
Yeah, good question. Okay, is anybody unclear about the top part? So for anybody who came in late, I really mean this. If this shows up on any online site, then nobody in the entire class gets any extra credit. Okay, so this cannot be posted anywhere online. You can't go to online resources. You can go to book resources and human resources, but you can't post it online. And if I find it online, then the offer of extra credit is out the window and the original scores stand. Okay, I don't think that's unreasonable. Okay, sure there's no more questions? Okay, so in that case, we can move on. Another thing you could do with that extra credit, like if you're really trying to make sure you understand it well and you know how to do it, you could work on it at home and then pop into the help center and say, can you look it over for me? Did I do it all right? And just have them have a look at it for you. That's another decent way to do it. So that should really help you. But you should be able to answer most of those questions based on all of the notes that we have. Okay, so last day we did a bunch of magnetic field stuff. We said that charged particles moving in a magnetic field feel a magnetic force. If the velocity and the magnetic field are perpendicular, then we end up with circular motion or cyclotron motion. And we can write an equation to express that. So we're going to keep going with that kind of circular motion stuff for today, and we'll talk about some applications. So this builds on a question we did at the end of last day. We shoot a charged particle, in this case an electron. We shoot it with this speed into the magnetic field shown. And we say here loosely what happens. On a test, this would be a better defined question. We'll go through it and we'll look at what's happening. So we're taking our electron. We know that it's a negative charge. It's being shot in horizontally. So there's our velocity. And the first thing we might think about is what is the motion of this charged particle going to be? So as soon as we get our charge moving in a magnetic field, it is going to experience a magnetic force. To find the direction, we apply our right-hand rule. The thumb goes with the velocity. The index finger goes with the magnetic field, so that's into the page. The extended middle finger is the magnetic force. That points up towards the ceiling. But your right-hand rule applies to positive charges only. Electrons are negative charges, so the result we get for the force has to be rotated by 180 degrees. It's going to feel a force that points down. The magnetic force and the velocity are perpendicular. When force and velocity are perpendicular, it leads to circular motion. So this is going to start to follow a circular path. So the path it will follow will be to deflect downwards and move in a circle, something like this. Okay, so conceptually that's what happens. So we'll say that it moves in a circle. Typically in a problem like this, the question could be, what is the radius of that circle? That would be a pretty typical question. So if we wanted to find the radius, let's say that question is posed to us, we would start with Newton's law. The sum of the forces on our electron is mass times acceleration. In general, the mass is so small that we're going to neglect the weight, so that's not going to come into play. The only force is going to be the magnetic force. Because it goes in a circle, we can say that A is V squared over the radius R. Our magnetic force, we know, is Q, the magnitude of our charge, times V, times B, times the sine of the angle between V and B. V is to the right, B is into the page. Those two things are perpendicular, so the angle between V and B is 90 degrees. So we've got Q times V times B, sine 90 is 1 equals M times V squared over R. The magnitude of the charge on an electron is the fundamental charge plus E. This equation is dealing with magnitudes. We do know an electron is negative, but we're dealing with magnitudes, so we put in the positive value. It's got a V here, a V squared here, so one of those divides out. So the radius of the path will be the mass times the speed divided by the magnitude of charge and the magnetic field. Put in your numbers. And the magnetic field size is given in the picture. That gives us a radius of the path 2.72 times 10 to the minus 5 meters. Okay, any questions? Okay, so this part is okay. So we know that if the electron comes in here, it will deflect and move in a circular path. So we could ask the question, what if we wanted the electron to go straight through? What could we do to make that happen? So that will be the next thing we look at. So before I pop up the next slide, what could we do to make that go straight? Any ideas? The magnetic force pushes it down.
By upward force?
We can apply an upward force. That's exactly what we can do. The kind of thing that has forces on charged particles is an electric field. So if we bring an electric field into the picture, we can get ourselves an upward force. If we can make it so those two cancel, that thing will go straight through.
Is that why electricity and magnetism don't get it? Or
That's not the reason. If we get through this in time, I will talk about why electricity and magnetism are actually the same thing. If we don't get through everything in time, you can come to my office and we'll talk about it. But yeah, electricity and magnetism are actually kind of two sides of the coin. Okay, so for our previous example, what electric field could we apply to make the electron go straight through? And there's a reminder of what we did in the problem. So we had an electron, that was our negative charge. It is moving forward with velocity v. We know that when it moves in this magnetic field with a velocity in that direction, the direction of the magnetic force is going to point down, Fb. If we want it to go straight through, we need to have an upward force. So let's draw that force on the picture. Because this is a charged particle, the kind of force that we need is an electric force. So let's get a couple of notes down here as we go. So if we want it to go straight through, that means no deflection at all. It doesn't go up or down, just goes straight. That means we need to have the net force on our electron equals 0. And again, we're neglecting weight because it's so tiny it doesn't make a difference. We know that our magnetic force is down. That means our electric force has to point up. Everybody good to hear? So, what does that mean about this direction of our electric field? Any ideas what way that's going to have to point?
the upward
Okay, first answer was upward. Few confused faces.
or downward, was it?
Okay, now we have up and down on the table. Okay, if we don't want to commit, why don't we just leave it for right now? Okay, let's keep thinking about it theoretically. Let's get into the math and see what happens. So the net force is equal to 0. I'm going to leave this as a vector equation because we decided we weren't totally confident in the direction of our electric field. So I'm going to leave it as a vector equation. So our magnetic force vector plus our electric force vector equals 0. Our magnetic force had a magnitude of E times V times B. We did this on the previous page. The direction is down, so that's why I have a negative here and a j hat. So our coordinate system is positive x to the right, y is up, and z is out of the page. Our electric force, so Fe, is our charge on our particle times the electric field. The charge of our particle is negative of the fundamental charge. Okay, so there's our electric force. Let's put that in our equation. I'm trying to solve for my E, so minus E times E equals E V B j hat. So I just brought this term to the other side. So then my electric field is E V B j hat divided by minus E. My electric field is minus V times B j hat. Okay, so my electric field points down. That's because of the negative sign right here. If the charge is negative, the electric force and the electric field have opposite directions. So if the force is up, the field is down. And the magnitude of the electric field is the speed of the particle times the size of the magnetic field. We might ask, how do we get that electric field in the picture? So where would that electric field come from? Basically what we could do is set up a capacitor. So if we wanted an electric field that pointed down, if we put a positive plate up here and a negative plate down here, then the electric field would point from the positive to the negative, and it would be constant. This whole setup is called a velocity selector. And what a velocity selector does is it shoots charged particles through crossed electric and magnetic fields. That's what we have here. Electric field is down, magnetic field is into the page. It shoots a particle through those crossed fields. Only particles with the right velocity, E over B, only those go straight through. Everything else deflects either up or down. So that's why it's called a velocity selector, because only charges with the right velocity will go on through. Okay, any questions? So let's get to work on another example. Okay, so this one is a bit longer. This is a velocity selector, so that's the first bit here. And then we also have what's called a mass spectrometer. We'll talk about that a little bit as we go through the problem. So what's going on here is that we have positively charged ions. We're emitting them from a source, so a positive charge is coming out of here. They're first passed through a velocity selector. It's got our crossed fields, and we know the size of the electric and the magnetic fields. Okay, so that's this part right here. We want to draw the free body diagram on a positive charge going through here, and we want to find the speed of the particles that can pass straight through, so that's those two parts. When it comes out of the velocity selector, it goes into a new magnetic field. The size of that field is called V with a 0 on it. They travel in a circular path, and they hit a plate 7.26 millimeters from where they started. We want to find the charge to mass ratio of the ions, which is what a mass spectrometer does, is it gives you the charge and the mass ratio. Okay, so let's jump in and get started. So for part 1, draw the free body diagram on an ion passing straight through the velocity selector. So we've got our positive charge in here, and we want to draw the free body diagram on it. I could draw in the picture, but it's awfully small, so I'm going to draw over here instead. So here's my positive charge. It's got a velocity moving to the right. I'm putting my velocity in the picture because I know I need my velocity to figure out the direction of the magnetic force, so I know the velocity is important. So my velocity is to the right, my magnetic field is into the page, my extended middle finger shows my magnetic force. I see that that points towards the ceiling. This is a positive charge, so my right-hand rule is for a positive charge. The magnetic force points straight up. So we use the right-hand rule to find the magnetic force. So there's our FB. And in brackets, we'll say we use the right-hand rule to find that. For our electric force, we know the electric force is the charge times the electric field. The charge is positive, so the force and the field have the same direction. The field is down, so the force is down. So there's our FE. We know that direction because FE equals QE, and Q is positive. Okay, so there's our free body diagram. Let's put in a coordinate system because we always put in a coordinate system. Everybody good with that part? Okay, find the speed of the ions, which can pass straight through. So we know that they have a magnetic force because they're moving. So let's put all of this stuff together. So because it moves straight through, the sum of the forces in the y direction is mass times acceleration in the y has to be 0. So it goes straight, so the acceleration is 0. The magnetic force points up, so we've got plus FB. The electric force points down, we've got minus FE. That has to equal 0. The size of our magnetic force is Q times V times B times the sine of the angle between V and B. V is to the right, B is into the page. Those two things are perpendicular, so the angle between those two things is 90 degrees. Minus the magnitude of our electric force, that's Q times E equals 0. So Q times V times B equals Q times E. Got Q on both sides of the equation, so we can divide both sides by Q. V equals E over B. This is the speed of the particles that can go straight through. In this problem, we do know E and B, so we can calculate the speed of those particles. E is 1 times 10 to the 6 newtons per coulomb. B is 33.3 Teslas. So that speed is 1.75 times 10 to the 4 meters per second. So anything with speeds higher or lower than that, those will deflect off and go either up or down. With exactly this speed, they go straight through. Everything else does not move that. Okay, are we good to hear? Okay, that's part 2 done. Part 3 says we come out of the velocity selector, we go into a new magnetic field which points into the page. We know the radius of the path, or we almost know it. We know the diameter, the radius is easy to find. Find the charge to mass ratio. So this bit is going to be like how we started the day. We have a charged particle moving in a magnetic field. The force and the velocity are perpendicular. It moves in a circular path. We can write down the equation for that, and we can figure out the charge to mass. Okay, so let's start in our new field. So part 3, we have our positive charge, and it moves through a half of a circle in a new field. We know that this distance is 7.26 millimeters. So the radius of our path is 7.26 divided by 2. 3.63 millimeters. And now let's do an analysis of our force. We know that the net force on our charged particle is mass times acceleration. This time, we're not in the electric field anymore. We're just in the magnetic field B0. We can put that on our picture if we want to. So the force that acts on our charged particle is the magnetic force, FB. It's going in a circle, so A is V squared over R. Our FB is our charge times V times B times the sine of the angle between V and B, that's 90 degrees, equals mv squared over R. We've got a V here, a V squared here, so one of our V's cancels. Sine of 90, that's 1, so we've got Q times B equals M times V over R. This question asks for the charge to mass ratio, so it wants to know what is charge divided by mass. So we'll cross multiply our M over here and our B over to the other side. Q over M equals V over B times R. V is the speed of the particle. We found that in the previous part, 1.75 times 10 to the 4. B is our magnetic field, B0. We are given that that is 0.1 Teslas. And the radius of our path is 3.63 times 10 to the minus 3 meters. Okay, now I have to pause just for a second, and I missed what I was supposed to do at the very beginning of this problem. So the electric field and the magnetic field were given, but at the last minute I did change them. So if you downloaded the notes, please do update this. I'm so sorry I didn't say it as we began. The electric field is 5.83 times 10 to the 5 newtons per coulomb. And our new magnetic field, B0, is 0.100 Teslas. Okay, so as you're studying and going through the notes, I don't want you to wonder where the numbers came from. It's because I changed them. This number for the velocity that we found, this is based on the new electric field. Okay, so I did all the math right, I just neglected to update the question. Sorry about that. Okay, so we'll come back to here. All of these numbers are what they're supposed to be. This gives us a charge to mass ratio of 4.82 times 10 to the 7 coulombs per kilogram. This sort of a thing, shooting charged particles into a magnetic field and measuring the radius of the circular path, this is something done by atomic physicists all the time. So you shoot particles in, and what you can learn just from measuring the radius is the charge to mass particle ratio. It's a way of finding new particles. If we were in a problem session, or if this was homework, I might ask you to identify this particle. So from the charge to mass ratio, you could actually figure out that that's an alpha particle, and that's a helium nucleus. Okay, on a test I wouldn't ask you that because you kind of need Google at your fingertips to figure that part out. Okay, any questions here? Okay, so there's a couple of similar problems that I'll just leave for homework, so you can do those for practice. now we'll get to talking about the next thing. So a demo we talked about last day, when we talked about there being a magnetic force on charges moving in a magnetic field. The demo we referred to was what you did in the lab with your motor lab, and we saw that when you turned on the current, those charges felt a force and your motor started to spin. And we put in a comment that moving charge is just current. So now we're going to bring in current and find an expression for the force based on current instead of just based on charge. So if we have a moving charge, we do know that the magnetic force, FB, is equal to QV cross B. That's an experimental result which is well studied, that can be measured and found. If we wanted to think about how this works, then V is a small distance divided by a small time, and that's crossed with B. If we look at this equation, we see here, well, why don't I just slide my delta T over? Delta T is just a scalar, so I can bring it over in front. Delta X cross B. This is something we can work with. So this is a charge moving in an amount of time. That's what we call current. So Q over delta T is our current I. And if our current travels along a wire, with length L, then delta X is equal to L, and then our magnetic force becomes FB equals I times L cross B. And so there's an expression for magnetic force on a current carrying wire. So moving charges feel a force, moving charges current, so current carrying wires feel a force. Right here, I and L, this goes back a little bit to my pet peeve about this textbook. Your book lists L as the vector, and that's absolutely fine. When it specifies the direction of the length vector L, it says it's the same as the direction of the current flow. Okay, so I and L are in the same direction. So you look at which way the current flows, and that's the direction of your length vector. You could also write I as the vector and L as a magnitude, doesn't matter, so it's the same. So this is how we would do it using the cross product. We can also do magnitude and direction, so we can also say, or the magnitude of the magnetic force is I times L times B times sine theta. Theta is the angle between L and B. And we would use our right-hand rule to get the direction. So with the right-hand rule, your thumb goes in the direction of the first vector, your finger goes in the direction of the second vector, and your extended middle finger gives you your result. So L cross B gives our force. So the same thing we were doing for QV cross B. So there's a picture of the right-hand rule that your textbook uses. Any questions here? So let's do a couple of conceptual examples. If we had this wire and we set part of it in a magnetic field, this is a little bit what your lab looked like. You had a magnet here and some wire above it. If we don't run any current through this wire, what would the force on it be?
Zero.
Zero. Okay. If I is zero, force is zero. So this one's not very difficult. FB equals zero. So no current, no force. For this one, our current is traveling up the page. So there's our current. What would the direction of the force on this wire be? So here's where we've got to use the right-hand rule. So your thumb is the direction of the current. So the thumb of your right hand should be pointing towards the ceiling. Then your B is into the page, so you have to extend your middle finger, and then you have to twist around your hand till you're shooting your gun into the page. Okay? You extend your middle finger, which way is that pointing? It's pointing over to this direction. So that's the direction of the magnetic force. So I cross B gives our force this way. There's FB. If we asked what the result of that magnetic force is, that wire would tend to bow out to the left of it. And so that's what that force would do. It would pull it to the left a bit. Okay, what if we had the current flowing downwards? We can do our right-hand rule here. So your thumb has to point down, so your thumb should be pointing towards the floor. Your index finger is into the page. Your extended middle finger shows the direction of the force. That's pointing towards that wall over there. So our force on this wire, FB, is out this way. And the wire would tend to bow out to the right. Okay, any questions? So let's do this in a different kind of example. So in this example, and this is going to be one with all symbols, a metal bar with mass M and length L is suspended from two conducting wires, here and here. So that's attached to a ceiling or something. We have a uniform magnetic field B pointing straight down. We want to find the angle of those wires when we run a current through the whole thing. So this is a three-dimensional view. The first thing in my inclination to do is draw an edge view because 3D pictures are a little bit hard to work with. So let's assume that we're going to look from edge onto the wire, and the current is flowing this way, away from us. In our edge view. So the wire is going away from us, and the current in the wire is going away from us. It is hanging off some sort of rope, a conducting wire, and the angle between that wire and the vertical is 0. And it is sitting in a magnetic field that points straight down. Everybody okay with the setup? The translation to the edge view? Okay. Yep.
What edge are you looking for from the first one?
Yeah, we're just looking from this end.
Is that an X on the tube?
Yeah, just showing that the current is going this way.
Wouldn't that be a dot rather than an X?
No, dot is coming at you because you're looking at the tip of the arrow. The X is the flights of the arrow going away from you. Yeah, so that's our notation. Away is an X, toward is a dot. Okay, so when we're looking at this, we know that it's a current carrying wire in a magnetic field. It feels a magnetic force. We know that it has mass M, so it has a weight. It's attached to a wire, so it's got some sort of tension in the wire holding it up. If we're thinking about these forces, the first thing we can do is draw a free body diagram, and then we'll try and work from that point of view. We'll use a free body diagram, or just start using laws. So in our free body diagram, you can draw it on here. I think I'm just gonna draw a new picture down here. First one I'm gonna draw is the weight. I know that the earth pulls it straight down, Fg. Then I'm gonna draw the tension. The tension is along the wire, so it comes up this way. Then we need to get our magnetic force. To get the direction of the magnetic force, we have to use the right-hand rule. So our thumb is into the page, that's the direction of the force. Magnetic field points down, so that's down towards the floor. Then the direction of the force is coming this way. Okay, so the direction of the force is that way. If you want to do it on your sheet of paper, your thumb goes in this way. And then my B needs to go down. It's starting to hurt my hand a bit, so I'm just going to twist my paper. My current is into the page. My B is down. My extended middle finger shows the force coming this way. Okay, so my magnetic force is this way. If you don't like using the right-hand rule, you can certainly do the math method. The current is into the page, that's the negative K direction. B is down, that's the negative J direction. So the magnetic force would be negative K cross negative J, which would give you negative I. Okay, so if you like the math way better, that's absolutely fine. After we do a free body diagram, let's show our coordinate system, and then we'll apply Newton's laws. So there's X, Y, Z. Newton's laws, this thing is hanging in place, so the sum of the forces in the X direction is mass times acceleration in the X, that's going to be 0. Sum of the forces in the Y is mass times acceleration in the Y, that's going to be 0. We're trying to find the angle theta, so let's start by writing down both of our equations. In the X direction, I've got an X component of my tension, Tx. And there's my Y component, Ty. This is my angle theta, so this is my angle theta. So my tension, the X component is opposite the angle, T sine theta. I also have my magnetic force, that's to the left, so minus Fb equals 0. Okay, so there's my force. Tension's to the right is positive, magnetic force to the left is negative. T sine theta, the magnitude of my magnetic force is I times L times B times the sine of the angle between the current and the magnetic field. Current's into the page, magnetic field is down. The angle between those two is 90. Okay, so you gotta be really careful with that angle in your expression. So T sine theta minus ILB equals 0. We can't do lots with this. T sine theta equals ILB. We're a little bit stuck. We can't solve this one for theta. There's just not enough information. So let's come to our Y equation. In our Y equation, we've got the Y component of the tension, T cosine theta. Downwards, we've got the weight, that's M times G, that equals 0. So T times cosine theta equals mg. This is something we can work with. We don't know the tension. A thing I think about when I see sine and cosine is that sine divided by cosine is tangent. So T sine theta divided by T cosine theta is something I would like to do. T sine theta is ILB. T cos theta is mg. Our t's cancel. Tan theta equals ILB over mg. To find our theta, we would just do the inverse tan. Okay, so given your current length of field and mass, you could find the angle that that would swing out to. You'd see as you turned your current up and down, you would change that swinging angle theta. So you could see that go in and out. Okay, any questions there? Yeah?
How is the angle the same if we're looking at a different view? Because isn't that angle when you're looking at it from this way, but then when you go down, it's from the other side?
Yeah, it's sort of hard to picture. So in your 3D view, so here's your wire right here, and the magnetic field points down. We turn on the current, and the thing swings out like this. Right, and that 3D view has got you kind of looking at it like this, and we're just going to twist it around so you look at it like this.
Okay.
Does that make it a little bit more clear? Yeah, the 3D pictures are hard to see. Okay, we've got 1 minute left, so we'll quit there. I have to run to my next class, so for the people who came late, can you please ask some of your neighbors what the deal is with the extra credit? And then come see me